Welcome to video 9.2 in our first Principles of Astrophotography series. In this video, we provide evidence that the full width at half max of unsaturated star profiles does not depend on star brightness and is therefore the same for all unsaturated stars in an image.
Yeah, this property makes the full width at half maximum especially useful as a measure of seeing resolution. It is in fact the standard measure of seeing resolution for astrophotography,
as we discussed in our previous video.
Yeah.
This video is based on section 9.2 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility.
On January 28th, earlier this year, I went out to Treasurton, Idaho, our Mortal 2 site, and I shot the M35 shoe buckle open cluster through our Celestron Edge HD 9.25. I wanted the highest resolution we could possibly get, so we used the longest focal length we have in our arsenal. And here's all of its specs. One spec that I'd like to draw your attention to is the full width at half max of the Airy profile for this telescope. So this is the minimum possible full width at half max that you can possibly get with that telescope. It's a diffraction limit of that telescope. It's the best you can do. And the pixel scale for the telescope camera combination is 0.3281. We took a bunch of frames and then we looked at it in PixInsight, and PixInsight subframe selector allows you to look at the full width at half maxes of the stars in the frame. And we looked at the 9 very best frames and the 7 worst frames.
Yeah.
And we're dedicating these 9 good frames to the 9 mortal men doomed to die. And the 7 bad frames to the 7 dwarf lords in their halls of stone.
Stone, yep.
Mm-hmm. So what I'd like to point your attention to is these numbers here, which will come into play later on in this video. First of all, the full width at half max of the good stack averaged 2.72 arc seconds. And comparing that with 0.5 for the Airy profile, you say, that's not very good.
Mm.
And in fact, comparing it with the seeing categories that we discussed in the previous video, that would fall into the poor category, which is between 2 and 4 arc seconds for the full width at half max. And so you're saying, that's not very good data, Boyd. And I'm saying, well, in my defense, in Treasurton, it was a windy night. And the wind is probably the reason why the bad stack is as bad as it is.
Yeah.
This is pretty much horrible.
Yeah.
And I think we had some wind still with the good stack as well. So not only are we seeing the effects of seeing the effects of seeing, but we're also seeing the effects of wind, which isn't technically seeing, which jiggles the mount around. That's not really atmospheric turbulence. It's just bad tracking or wind or whatever. All these sort of things sort of add up to the full width at half max, and you deal with it. Okay, so here is an image of the good stack of the M55 shoe buckle cluster, and I've put circles around 6 stars of decreasing brightness. So the brightest star we have is star A, which is a 6th magnitude star. And then B, and then C, and then D, and then E, and F. You should be able to barely see on the screen a tiny little dot representing star F. Now on the next slide, I'm going to show you the bad stack and ask you to maybe focus on perhaps star B when I click the button, and ask about how its size changes. 1, 2, 3, go. Okay, so
It's bigger.
it got bigger. The size of those stars in the image got bigger. The full width at half max is 6.38. In a future video, we'll talk about the actual star sizes that depends on how you stretch the image, but not today. So here is a list of those stars. These MV values are their visual apparent magnitudes, denoted by M, stands for magnitude, and visual stands for V, that stands for visual. This is the first time we've talked about star magnitudes in this series, and for the purpose of this video, what you need to know is that the bigger the magnitude, so a magnitude 15 star is dimmer than a magnitude 6 star. So as the magnitude goes up, the apparent brightness goes down. And it's on a logarithmic scale, which we discuss in full in the book if you want the details. These are the centroid positions of this. Well, a centroid is the calculated center of the star. In fact, why don't you read that for us?
It's the estimated center point of a star's image on a sensor. You're welcome.
Thank you. So in these images, there's an XY coordinate system. Here, forget if y is measured up or down, but it doesn't really matter. And the center of that star is called the X naught, Y naught, the centroid of that star. And it's calculated based on how intense the coloration is of all the pixels around it. It's just a simple algorithm, which is exactly the same algorithm that you use to calculate the center of mass, if you wanted to know that. Like in our airplane days, use the same formula to find the centroid as you do for center of mass.
Interesting.
Pretty cool. So those are centroids of these stars. These are the ADU values at the star centers. AKA the star centroids. Now you might notice that all of these 65, 5, 35. You might say, well, that's weird. Why all those are the same? Well, the short answer is that our sensor is a 16-bit sensor, and a 16-bit sensor allows ADU values between 0 and 2 to the n minus 1. And 2 to the n minus 1 for a 16-bit sensor is 65, 5, 35, as we talked about in the previous video. So all of these are saturated.
So how does that relate to our sensor, like well depth?
It means that each of those centers of those stars reached the well capacity. They couldn't, yeah.
There was no more the sensor could take in because it was full.
That's right. So the photons come in, hit that pixel, and then the number of photons that come in is proportional to the number of electrons in that well, and the number of electrons in that well is called the well capacity, like we talked about before, and that well capacity is around 50,000. I think it's 54,000. I forget what the exact number is. Yeah. Once it fills up, you're done. And that's the full ADU value.
So that's saturated. When you're saturated, your well depth is fully filled, and your sensor cannot get any more electrons.
Can't take any more in. Okay, I think that's what we need to say about that slide. This is a diagram of how we calculated star profiles. So if this is the centroid, as we talked about before, and this circle dotted line circle is 5 pixels away from the center. So here's the pixel size.
Yeah.
And so if you look 5 pixels out, between 5 and 7 pixels out, you use information between both of those dotted line circles to determine what the, so this is 5, that's 6, and that's 7. So what we're actually looking for is the profile star intensity on that circle of diameter 6. And we're going to use the information from all the pixels between 5 and 7 in a weighted fashion. So if, for example, right here, let's see, trying to find one, yeah, right there, that pixel would be counted the heaviest of all, but this pixel wouldn't be counted at all because it's 1 pixel away, the center of it's 1 pixel away from the one that we're looking for. So we use a weighted average process to determine the profiles. And the reason we wanted to do this with some care is that we wanted to really look carefully at what those star profiles look like and ask the question about whether the full width at half max depends on the brightness of the star. And you might say, well, why are you interested in that? And the reason I'm interested in that is that the full width at half max is used to characterize the seeing. And so do you have to, when you're talking about the full width at half max, do you have to worry about how bright the star was? Well, hopefully not. You'd like to just be able to say, well, it's valid for any unsaturated star.
Yeah.
Okay, so that's a calculation technique. And this is what we got for the good stack. The n equals 0, so we're measuring, it's just like in the previous diagram where we're measuring distances from the centroid out further and further distances. So this n equals 0 corresponds to the centroid. And here n equals 5 corresponds to, 5 pixels away from the centroid. Now what you can see here for stars A, B, and C is that they come up and then they saturate. And where do they saturate? They saturate at 65, pi 35. So back to here, you can see in the good stack, stars A, B, and C are all saturated in the center. So had the well capacity of our sensor been higher than 50,000, then A, B, and C would have continued on up and then reached their peak up there. Now D, E, and F are not saturated. So A, B, and C are saturated. D, E, and F are unsaturated. And that's what that, when we use the word unsaturated, that's what we mean about full width at half max. It's going to be the same for all unsaturated stars in an image. All right, well, let's take a look. Here's star D. It reaches a peak close to 30,000, and at about close to 15,000, it reaches its 15,000 is its half max, and that's at a pixel, about pixel 4.15. What about star E? Its maximum is around 6,000 or 7,000. Here's where it reaches half its maximum. So it's at least reasonably believable that star E reaches its half maximum at the same place that star D does. But we're going to do a more careful analysis to see if that's actually true. So what we're going to do in this next slide is to scale each of those 6 star profiles until they match each other as they go out toward infinity. So if we want star A to match star B out here, we're going to have to lower star A's profile until it matches star B. And if we want C to match B, then we'll have to raise it. So basically, we're just going to multiply all these numbers for each of these 6 by different scaling factors so that they'll overlap on each other. And this is what we get. So star A, here now star A is way down here at the bottom, but it does match everybody else out as you get further and further away. Here's star B, star C, and then D, E, F, and G. And you can see that they all overlay quite well. Now G is not a star. G is a model that we created called the Moffett profile, which clearly matches these star profiles quite well. It has some adjustable parameters, and we talk more about it in the book. But the important point here is that stars D, E, and F overlap with each other really well over the whole range of distances from the center, and they all reach their half max at that same number of pixels of 4.15.
Yeah.
And had stars A, B, and C not been saturated, then we can reasonably expect that star B would have maybe followed that same profile, although we'll never know.
Yeah.
So this is a number of pixels. It's the half width at half max. So this is the half width at half max. So here's the half max. This is the half width. If we'd wanted the full width, we would have had to gone and reflected the thing over to the other side and looked at the other side of the star. And just using the pixel scale equation, which we talked about in a previous video, you can relate this number of pixels to the number of arc seconds in the sky. That's what the pixel scale equation does. Okay, here's the bad stack. And as you can see, stars A and B are saturated. Stars C, D, E, and F are not saturated. And it looks like at first glance, here's the maximum that C reaches around 54, 55,000. And then around 27,000 it reaches its half max. And this half width at half max for the bad stack is 9.73 instead of the 4.15 for the good stack. And the corresponding full width at half max is 6.38. So then collapsing all of these onto the same curve, you get a nice matching up. There's some wonkiness here at their peaks, partly because star F is really, really dim, and the statistics for calculating the profile really close to the center get pretty not very good statistics. You only have 1 or 2 pixels or 3 or 4 that you're averaging to find the star profile. But it's at least believable that these match up quite well over the whole range, and had A and B not saturated, they might also have matched up pretty well.
Principle 118, full width, half max, and brightness. The full width to half max seeing resolution does not depend on star brightness.
This is, I think, the final graph that we want to show here. A is the Airy profile. For that telescope, the Celestron Edge HD 9.25, and its half width at half max as measured in pixels is 0.76. Then this is the B is the good stack, and C is the bad stack. So what's interesting about this one, to me at least, is just how far we are in taking these long exposure photographs from capturing the maximum possible resolution.
We're so far. Yeah.
Yeah, I mean, this curve B, even the good stack, we're talking about a full width and a half width at half max of 4.15 instead of 0.76. It's kind of embarrassing.
Yeah. We need less atmosphere.
Yeah,
Less
or maybe one of us should move to Peru in a couple of weeks.
Wait. That's a good idea.
Maybe we will. We're going to be, my wife and I are going to be at 13,500 feet in a place called Junin, Peru, Junin, taking images of Rho Ophiuchi, for sure, and hopefully a few others. We're going to take a really wide field. We got an SQA, Ask Our SQA 55 on order to
On the
take
way,
down with us.
hopefully.
Hopefully get it in time. But hopefully we'll have less atmosphere there, and maybe we can do a little bit better on the resolution front.
Okay.
Thanks so much for watching.
And we'll see you next time.